10.3 is solving trigonometric equations, and this is going to be taking a different type of route than what we've been doing in the past with 10.1 and 10.2. Once again, as a reminder, 10.1 and 10.2 were about verifying trig identities. We were looking at those identities and subbing certain expressions in, certain expressions out. And what we would be doing is just working with one type of an expression and rewriting it and rewriting it and rewriting it in some sort of equivalent or equal form. So now in 10.3, this is solving equations. So this is where whatever you do to one side, you have to do to the other. It's where we're actually trying to change one side. So we're actually going to be stripping down what it says right here. Our goal is to strip down an equation, one side of our expression, to one single trig function. And as we are in the process of doing that, you're going to be adding something to both sides or subtracting something from both sides. So this is very different from 10.1 and 10.2 in that whatever you do to one side, you have to do to the other. Our other goal is to connect it to inverse functions in the past, but we're going to see that it's somewhat limited and your calculator can only help you so much here. Alright, so we're going to consider this following equation, and we're going to have to solve for this. So remember, when you're solving an equation, it means that you're trying to find for what value of this variable that we could input here will make this equation true. So what angle will go, when you take sine of an angle, multiply it by 2 and subtract 1 from it, well, you get 0. So a little bit tough, I know. So I'm actually going to graph this first. And what I want you to note is we have a multiplier to the overall function, so not directly attached to the x, but to the overall function. That is our amplitude. So we have an amplitude of 2. Alright, here we have no multiplier onto the x except for 1. We have sine of basically 1x. So our period has not changed. There's no period or horizontal stretch or shrink. So it's just going to be 2 pi is the typical period for sine. This got a lot of you on the quiz. We have a subtraction of 1 here, but it's not directly attached to the x. There would have to be parentheses around it for that to be the case. So yes, it kind of looks like it, but because there's no parentheses around it, we're saying it's not directly attached to the x. It's not sine of x minus 1. It's just sine of x and then subtracting 1. So we have it's vertical. It's vertically down 1. Okay, so I'm going to go ahead and sketch that. Go to 2 pi. Here's my pi, and then of course we quarter it for our key points. So here are our key points that I'm going to have to keep track of. Those are where the interesting things are happening. So now I also need to know that I'm vertically down 1. So this is going to get a little bit, I'm going to make my scale tick marks kind of far apart. Here's 1, here's 2, oh man. Here's 3. So I have -1, -2, -3, and I did have to go all the way down to 3 because of my amplitude. I'll have to go all the way to 1 because of my amplitude as well. So here our midline, our horizontal line, everything about our graph has been shifted down vertically, including that center line that used to be on the x-axis. So that's where I'm going to be starting, and because this is sine, at the start we're going to start at the midline. Oops. Okay, at the first key point for sine, the typical shape would go up to 1 and then back down to the center line, down 2 because of that amplitude, it goes down to its minimum, and then on the fourth key point it goes back to its center line. So here, whoa, is our kind of sine shape, although it should be more flowy, of course. So it says solve this equation and understand this, that this would go back as well. So we would be looking at something, sorry, but there we have it, and this of course would be going forward forever as well. And it says find the values of this, what I've been graphed, when it's equal to 0. So basically what I'd be looking for is that point right here, this point right here, this point right here, and this point right here. But what you have to understand is, first of all, my graph is hardly perfect. In fact, it's really bad. But on your paper, if you were looking at this, what you would have to realize is they might not lay on key points. So what exactly are those? So you could, of course, graph this and figure out, all right, let's solve it for where does it cross my y equals 0 line. So when does this whole function equal 0? And they would be at those points, but we can also do this algebraically. So when solving equations, what I want is to get this sine of x, this single trig function by itself. So you're going to be doing the order of operations backwards, so SAD, MELP, and asking yourself, is there any subtraction or addition not inside of parentheses? So yes, there is. I'm going to undo that. So we get 2 sine of x is equal to 1. Now, is there any division or multiplication not in parentheses? And yes, there is. So I'm going to undo those. Sine of x is equal to 1/2. So now what this becomes is the question of, all right, what angles on that unit circle would get me 1/2 for my sine? So I really do hope you're getting used to using your unit circle, and sine is the y values. So it's when you would go far over that special triangle where you would go the longer leg up and then the shorter leg up, which is 1/2. So we're using that square root of 3 over 2 gamma, and then the 1/2 height. So this is one of those 30, 60, 90 triangles. So one of those will be 30. Another of them would be over here. And this right here is 30 closer to 180, but not quite, so it's 150 degrees when you look at that. Okay, so those are two possible angles. Alright, so I'm also going to show you what this looks like. I just graphed the basic sine function, and here it is. And what we will notice is we're interested in where it's equal to 1/2, so approximately right about here. Okay, so here's one of those solutions, here's one of those solutions, here's another one, here's another one. And what you will notice is, once again, you would have to actually kind of trace these down and see, alright, where are these points happening? And what I have done is I've gone ahead and separated my pi radians into 6 equal portions, and you can kind of see, yeah, it's happening at the 1 pi 6th. It's also happening at the 5 pi 6th. So here are solutions. But we also have to understand that this is going to repeat 2 pi down the line, right? So not only do we have pi over 6 as one of our solutions, but we also have plus 2 pi. Okay, and then if this 2 pi happened again down the line, well, we'd have that very same point. We'd have sine of that angle equaling 1/2 again. So it's going to be plus another 2 pi. So basically, as many 2 pi's as you want to add, these are all going to be coterminal. They're all going to, it's like this on your unit circle. You'd be going up 30 degrees, okay, or opening an angle 30 degrees, but you have to realize that if you went around the circle 2 pi, so for that total period, went around again, all of those have the same sign. It's sine of 1/2. It's a y value of 1/2 because you're on that same exact point. Same for this. Not only is x equal to this pi 6 plus 2 pi n, but x is also equal to that 5 pi 6 plus 2 pi n. Okay, so these are all possible solutions. One thing that I do want to say is your calculator would be restricted. If you look at this and go with that, continuing on that algebra route, and you would say, hey, I could just take the inverse sine of sine of x, because you know, that's how we undo trigonometric equations. So you would have to take sine inverse of 1/2. On my calculator, when you do that, you will get 30 degrees if you do it in degrees, and then you will get 0.52359 if you do it in your calculator in radians, because that is pi divided by 6. But once again, that's because inverse sine is restricted. Remember when we were back in that last chapter, we were talking about how sine has been restricted to only this much. So in other words, also it's from negative pi halves to pi halves. So what your calculator is going to give you is only this option. Because remember, in your calculator's mind, what a function is, it's for every input there is exactly one output. But what we're doing when we're solving is there's an infinite amount of outputs that's possible in actually solving for the value of x here. There are very many possibilities for x. So that is the restriction of your calculator. You can't just do the inverse functions. They're only going to give you one out of the many. In this process, once again, I need you to use your unit circle, so I guess I will put a 2 under this for the steps or the process that you're using. So first thing, when solving for equations, get the single trig function by itself. Then what you're going to want to do is use that unit circle to your advantage. You're going to try to find all possible solutions on your unit circle. You're not going to just do the algebraic inverse sine way. Okay. So get it by itself, then use your unit circle to identify what angles will make that equation true. And then consider the period and tag on all solutions if asked for. So once again, when we were looking at that 2 sine of x minus 1, what you have to look at is, for this particular equation, what is the period? Well, the period is, because it was that 1x, it would just be 2 pi divided by what's being multiplied onto x, which is our b. So 2 pi divided by b, which is in this case 1. So that's our period. That's when we found our solutions, which were the pi sixths and the 5 pi sixths, and we tagged on that 2 pi, that period, times however many times we wanted to go around, plus 2 pi n. So there is how you would answer that problem.